Hi there, thanks for joining us for I think it's going to be the third and last video for chapter 1. In the last video, we talked about the drawing Lewis structures as well as resonance forms. And I would say resonance is probably one of the most important topics that you learn in this half of this semester. So I would say, like, definitely go over that and make sure there's nothing that you didn't understand. And more importantly, more important than the lecture videos, I think, would be that you would work on homework problems that involve resonance. One of the things you notice about organic chemistry is it's not a subject you get better at by listening to good lectures or watching like really well crafted videos. Even though those things might help you feel like you understand something, the only sort of meaningful learning I think happens in organic chemistry when you do problems and solve them. So I would just encourage you to do that. But moving on from where we left off in the last video, and I kind of apologize for the last two videos being a little too long. Usually I try to keep it between 20 to 25 minutes, more towards 20 minutes. And the idea is that two of those videos would replace a 50-minute lecture during class time. So that's kind of the idea. But this third one should be fairly short, I hope. And where we left off, we were talking about drawing resonance forms, and we just talked about 4 different rules, right? That help you determine like which resonance form is the most important one or the major contributor to the overall structure of that molecule. Now, when you are drawing Lewis structures or even a resonance form, sometimes you're going to have to resort to what you might consider like weird structures, and those are the exceptions that we might want to go over that you'll encounter throughout the year in organic in our class. So one of those would be radicals, right? Like when you have unpaired electrons on an atom, like if you have a methyl radical or nitrogen radical. Fortunately, we're not going to encounter any radical compounds or intermediates until the end of the semester, but you will. Sometimes you encounter structures that do not meet the octet, like when we talked about hybridization, we may have discussed the beryllium hydride or something like that. The beryllium compounds or boron compounds, those tend to not meet the octet, and yet these are very legitimate Lewis structures because this is actually what the molecules look like. So those exceptions usually tend to occur with the first few columns of the periodic table, especially the second and the third group. When you go beyond the second row in the periodic table, you'll begin to encounter situations where an atom has expansion of octet in that you have more than 8 electrons on an atom, and that's okay because they have not only s orbitals and p orbitals, which total they can only occupy or accommodate 8 electrons maximum, but they also have d orbitals, right? Third row and below elements have d orbitals. And for that reason, they can have more than 8 electrons, and that's perfectly fine and natural, or I should say, low energy, right? So here's an example. Sulfate or sulfuric acid, right? Or if you think about the corresponding ion, sulfate, because sulfuric acid is a strong acid, right? You could think about the conjugate base a bit. Each of these is a valid Lewis structure, and you could say resonance forms. Like this is probably the most straightforward Lewis structure you might draw, but when you do, you're going to have to put two negative charges on these two oxygens, and you're going to have to put two positive charges on a single sulfur atom, which is a bit awkward. Whereas if you draw basically double bonds between this oxygen and that sulfur, while sulfur would have to accommodate 12 electrons, but you technically have no formal charges in the structure. Right? That becomes even more maybe obvious when you draw the sulfate ion structure, perhaps, but these are two resonance forms of sulfate ion. But actually, can you tell which of these two is preferred? It is the one on the left because of the rule number 3 and 4 of the resonance rules that we talked about last time. Now, those structures, of course, included what we would call formal charge, right? And that is a term that describes in a given structure where the actual charge lies, or which atom of a molecule has the charge. But the overall molecule that does have the charge, we would call those ions, right? And within an ion structure, the actual charge might be localized on an atom, and that's what we call formal charge. Okay, and usually the atom having a formal charge means that's sort of the reactive atom, as in it's not a stable atom. And that's, by the way, is the reason why we care so much about formal charges on structures in organic chemistry, because those are the atoms or the functional groups that typically do the reacting or reaction, because they're the reactive or not stable atoms. And how do you figure out the formal charge? Well, you have to compare the number of valence electrons that should be on an atom, and you compare that to the number of valence electrons that are actually on that atom, right? That's the comparison that you should do. It's kind of like this cookie sharing situation, and determining formal charge would be analogous in this situation to like how much of a freeloader you are and how much of a sort of contributor you are, right? Like, let's say Elma has these two cookies. I almost said electrons, but he brought two cookies to the table, and of course at a table with a cookie monster, you're going to probably have to share those two, one each, which means that Elmo is going to have a formal charge of +1, and Cookie Monster would have a formal charge of -1, and that would be calculated by subtracting how many cookies you actually do eat from how many cookies you brought to the table. Okay, hope that makes sense. So -1 charge means you're kind of a freeloader, like you're taking up electrons from others so that you have more electrons than you should have, like you deserve, more than you deserve. Plus charged species or atoms, or formal charged atoms, they brought to the table or to the molecule more electrons than they kind of have control over. So they kind of ripped off a bit. You know, they got ripped off a little bit, but that's positive charge. Okay. So let's consider this particular structure and see if we can assign the formal charge. And I'm spending a lot of time on this just because it's one of the most important things in organic chemistry, right next to resonance. So how do we do this? Well, carbon molecule, atom in this structure should have 4 valence electrons. That's how many he brought to the table. Okay. Now, the carbon actually has 8 electrons around it because it has 4 bonds, but to its name you could say he only has 4 electrons still, because each bond is 2 electrons worth, but it's as though oxygen has custody over this one electron, carbon has custody over that one electron. Same with the hydrogen. Hydrogen still has kind of a custody over one electron. Carbon has custody over one electron in this bond. So really, carbon has to his name really only 4 electrons. Hope that makes sense. Okay. So carbon should have 4 electrons because that's how many electrons it brought to the table, and it actually has, to its exclusive control, 4 electrons. So it's neutral, right? Like there's no formal charge. However, when you look at the oxygen, remember oxygen is in the 6th group in the periodic table, so it brings to the table 6 valence electrons. Now, if you look at the oxygen carefully, it has 8 valence electrons because everything meets the octet here, but it has exclusive control over the 6 lone pair electrons here, and then 1 of the 2 electrons in the shared bonding electrons, which means oxygen has to its name in this structure 7 electrons. Okay, that means it actually has 7 when it really should have had 6. So he's like this freeloader. He's kind of like a cookie monster. He got to have an extra electron. So this oxygen gets a -1 formal charge. Now, like we said, practice is the most important thing in organic chemistry. So I would encourage you to pause the video here for a minute and see if you can assign the formal charges to these structures using that same strategy. Okay, and the goal is hopefully this becomes like a second nature to you eventually, but pause the video and see you in a bit. So hopefully you had a chance to assign formal charges to all these. The first one here with the hydronium ion, I hope it makes sense that this has a positive charge, because the oxygen should have 6 electrons. That's how many it brings to the table, and yet it has to its name really only 5 electrons here. 2, because those are not shared, right? And then 1, 2, 3, 5. I hope this doesn't confuse you, but it does meet the octet because there's 8 electrons that the oxygen has access to, but to his exclusive control, so to speak, he has custody over only 5 electrons. So this would have a positive charge. Now in the next structure, if you look at the carbons, because it has one other thing you could figure might be helpful to you. Carbons, we said, should have 4 bonds, right? When an atom has the number of bonds that it should have, usually that does not have any formal charge. So these 2 carbons are neutral, yet the nitrogen, if you look at it, right, it has 4 lone pair electrons and 2 bonds. So it has to its name 4 lone pair electrons, exclusive control, and 2 bonding electrons, 1 each from the 2 bonds. So he has to his name sort of 6 electrons, in a sense. If I realize I'm kind of gendering these elements, but nitrogen has 6 electrons here, but he brought to the table only 5 electrons. That's the valence electrons. So nitrogen is kind of a freeloader here in this structure, meaning it has a negative charge. This oxygen again has to its name 5 electrons when it should have 6, so he's kind of getting ripped off a bit by 1, so it's a positive charge. Now these 2 carbons, they do not have the normal number of bonds. Right, that should alert you to the fact that it's going to have a formal charge. Right, this carbon here has to its name 5 electrons. Hope that makes sense. 2 lone pairs because those are exclusive to carbon, and 3 from the 3 bonds. So that's 5 electrons. Okay, so it's a negative charge, and this would be the opposite of that. It's positive charge. This oxygen, it's got 5 electrons when it should have 6. It's positive. This aluminum should only have 3 electrons, and yet it's got 4 from the 4 bonds, so it's got a negative charge. And this chlorine has 4 lone pairs and 2 from the bonds, so it's only 6 when it should have 7, so it's got a positive charge. Now in this structure there's also 2 charges. This nitrogen only has 4 electrons when it should have 5, so it's positive, and this oxygen has 7 when it should have 6, so it's negative. So hopefully that makes sense to you. And again, these things matter because usually the atoms that have the formal charges, that's where the center of reactivity is, because those are the reactive atoms. And in our class for most of the year we're going to be considering different organic reactions, and the way to know where the reaction is going to happen, we need to know where the formal charges are. Now as opposed to formal charges, we also consider partial charges, because some covalent bonds are not equally shared electrons, right? Because there's difference in electronegativity, and so for that reason some bonds do have ionic or polar characteristics to them, and I hope you're familiar with that nuance. For instance, in the structure in the left, carbon is more electronegative than magnesium, and bromine is also more electronegative than magnesium. So you could distribute these partial charges, which is depicted by the delta signs. Delta something usually means, well, almost all, your delta plus or delta negative means partial charges. It's not that there's a full charge there, but there's a negative characteristic on this carbon, positive characteristic on this magnesium, and so forth. And see if you can pause the video and distribute partial charges here on this molecule. So that would be the distribution of partial charges. Again, it's due to each of these bonds being made by 2 elements with different electronegativity. And hopefully you guys remember how to tell the electronegativity trends by looking at the periodic table. If you're not familiar with that, you should definitely review that. And this is the end of the 3rd video in chapter 1.